Welcome back to Mr. Vaughn's classroom, where math is made easy. Before we get started on today's lesson, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and engage with a comment below. In this video, we're going to look at Unit 7 on quadratic equations, Lesson 21, Sums and Products of Rational and Irrational Numbers. The learning goal today: let's make convincing arguments about why the sums and products of rational and irrational numbers always produce certain kinds of numbers. We have 3 learning targets for this lesson. When we get done with the practice problems, we'll come back and review these again and make sure you've learned everything you need to before moving on to the next lesson. Learning target number 1 says I can explain why adding a rational number and an irrational number produces an irrational number. Learning target number 2 says I can explain why multiplying a rational number other than 0 and an irrational number produces an irrational number. And learning target number 3 says I can explain why sums or products of 2 rational numbers are rational. Our glossary term for this lesson continues to be the quadratic formula. The formula itself is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In order to use the quadratic formula, you need to have a standard form quadratic equation, and you need to have that equation set equal to 0. Once you have that standard form quadratic equation set equal to 0, you can identify the values for a, b, and c. A will always be the coefficient in front of x squared. B will always be the coefficient in front of x. And c will always be the constant, the number by itself. Once you have those values, you can simply substitute them into the formula and complete the math to find your solutions for x. Now we can begin the practice problems for Unit 7, Lesson 21. Practice problem number 1. Consider the statement, an irrational number multiplied by an irrational number always makes an irrational product. Select all the examples that show this statement is false. So, the first thing we need to notice is that they want an irrational number multiplied by an irrational number. Well, a has square root of 4, and that is a rational number. And it's being multiplied by the square root of 5, which is irrational. So this would not prove the statement false because it doesn't fit the description given by the statement. When we look at b, we have square root of 4 and square root of 4. This is actually a rational number times another rational number, because the square root of 4 is 2, and that can be written as a fraction. So b would not help prove the statement false because it's not 2 irrational numbers being multiplied by each other. Now, if we look at c, Square root of 7 is irrational. And since it's square root of 7 times square root of 7, that is irrational. But if you take the square root of 7 and you square it, then your answer is going to be 7. And 7 can be rewritten as a fraction. So this actually proves the statement false because we multiplied two irrational numbers together and we got a rational number when the statement said that it would always make an irrational product. Now we're looking at D. D has 1 over the square root of 5. Since the square root of 5 is irrational, then 1 over the square root of 5 is irrational. Now we're multiplying that by the square root of 5, which is also irrational. But if we did that, 1 over the square root of 5 times the square root of 5 would equal the square root of 5 over the square root of 5, and anything divided by itself is 1. 1 can be rewritten as 1 over 1, therefore it is rational, and D would also prove the statement false. We took two irrational numbers, we multiplied them together, and we got a rational product. Now we look at E. Square root of 0 would not be considered an irrational number because the square root of 0 can be rewritten as 0 over 1, or really 0 over anything. So since it can be rewritten as a fraction, this is actually a rational number multiplied by an irrational number. Therefore, it doesn't prove the statement wrong because it doesn't fit what the statement is claiming. Now we look at F. Here we have the negative square root of 5 times the positive square root of 5. This is an irrational number multiplied by another irrational number. And if we actually did this, negative square root of 5 times positive square root of 5 is going to result in negative 5. And negative 5 can be rewritten as negative 5 over 1. Since this can be written as a fraction, this is a rational number and proves the statement false. And finally, option G, we have square root of 5, which is irrational. And we're multiplying that by the square root of 7, which is also irrational. But if we do this, we're going to get the square root of 35. 35 is not a perfect square, so if we tried to put this into a calculator, we will get an irrational number. So this one would actually prove the statement true, and that's not what we wanted. So on this practice problem, statements C, D, and F all prove the original statement false. So it is not true that an irrational times an irrational will always create an irrational product. There are times when it will create a rational product. If you have any questions about any part of this practice problem, please leave a comment below, and I'll get back to you with any help that I can offer. Practice problem number 2. Here are the solutions to some quadratic equations. Decide if the solutions are rational or irrational. So the first one that we have is 3 plus or minus the square root of 2. 3 is a rational number, but square root of 2, because 2 is not a perfect square, when we put this into a calculator, gives us that never-ending, never-repeating decimal. So that is going to be irrational. And if we want, we can go ahead and put it in a calculator just to check. But 3 plus the square root of 2. And here we see that we get an irrational number. Next one that we have is square root of 9 plus or minus 1. Square root of 9 is plus or minus 3, so that is rational. One is rational. And if you wanted to double check, you could say the square root of 9 plus 1, we get 4, which is a rational number. The next one that we have is 1/2 plus or minus 3/2. 1/2 is a fraction, so that is rational. 3/2 is a fraction, so that is rational. And if we tried to put it in a calculator, 1/2 is 0.5 plus 3/2, which is 1.5. The answer is 2, so that is a rational number. The fourth one they give us is 10 plus or minus 0.3. 10 is a whole number, which can be written as 10 over 1. So that is rational. 0.3 is a decimal that ends, so that can be rewritten as 3 over 10. Therefore, that's rational. And if you put it in a calculator, 10 plus 0.3 is going to be 10.3. That is a decimal that ends, therefore it is a rational answer. The fifth one they give us is 1 plus or minus the square root of 8 divided by 2. Well, this is going to be 1/2 plus or minus the square root of 8 over 2. 1/2 is a fraction, so that is obviously rational. But square root of 8 is not a perfect square. And if you put it in a calculator, you see that you get an irrational number. And if we tried to put that in a calculator, if we say 1 plus the square root of 8 divided by 2, we can see that we get a never-ending, never-repeating decimal, so that is an irrational answer. And the last one they give us on this problem is -7 plus or minus the square root of 4 over 9. Well, this becomes -7 plus or minus the square root of 4 over the square root of 9, and those are both perfect squares. So this becomes -7 plus or minus 2/3. So that means we have a rational number in -7 because it can be rewritten as -7 over 1, plus or minus 2/3, which is a fraction, therefore it is rational. And if we tried to put it in a calculator, we could say 2 divided by 3 plus -7 equals -6, but notice that the 3 repeats itself. That is -6 1/3. Because we can write it as a fraction, that is a rational answer. So notice what happens here. Every time we add or subtract two rational numbers, we always got a rational answer. But as soon as we tried to add a rational number and an irrational number, we ended up with an irrational sum. If you still have any questions about any part of this practice problem, please leave a comment below and I'll get back to you with any help that I can offer. Practice problem number 3 is going to be the last practice problem for this lesson. Find an example that shows that the statement is false. Number 1, an irrational number multiplied by an irrational number always makes an irrational product. This one is pretty simple. If you take any non-perfect square root, you're going to have an irrational number. But if you multiply it by itself, then you are squaring the square root, which cancels each other out and leaves you with the number under the square root symbol. So let's say we took the square root of 2 and we squared it. Well, the square root and the square cancel each other out, and this equals 2. Therefore, we had an irrational number multiplied by an irrational number, which was itself, but we got a rational product. So that proves statement number 1 false. Statement number 2. A rational number multiplied by an irrational number never gives a rational product. So there is one way that we could do this. We could say 0, which is a rational number because it can be rewritten as a fraction with 0 on the top and anything on the bottom. We can multiply that by any irrational number, such as square root of 2, and I'm going to get 0 for an answer. So this is a rational number multiplied by an irrational number, and my answer is going to be a rational product. For number 3, adding an irrational number to another irrational number always gives an irrational sum. Now, if you look back at number 2, you'll notice that there is what we might call a special case rational number, and that is 0. And we're going to borrow that to answer number 3. Because what we need to do is to take two irrational numbers, add them together, and get a rational sum to prove it wrong. And the way that we can do that is by adding opposites, because opposites will add together to equal 0, which is our special case rational number. So we could take square root of 2 plus negative square root of 2. These opposites are going to add together and equal 0, which means we took an irrational number, we added it to another irrational number, and yet we somehow got a rational sum. And that's because of that special case rational number that is 0. So I hope that everything I've gone over in this lesson makes sense to you. If you still have any questions about anything I did on these practice problems, please feel free to leave a comment below and I'll get back to you with any help that I can offer. Now, before we end the video, let's go back, review those learning targets, and make sure you understand everything you need to before moving on to the next lesson. Reviewing the learning targets for lesson 21. The first one says that you should be able to explain why adding a rational number and an irrational number produces an irrational number. And this happens every time. The reason is, if I have a rational number, then I'm adding something that can be written as a fraction. But if I'm adding an irrational number, I'm adding something that cannot be written as a fraction. So I would need to change the rational number to a decimal. We're going to take that rational decimal and we're going to add it to this irrational decimal that doesn't repeat itself in a pattern and it never ends. And so when we add them together, that's going to result in a decimal that does not repeat in a pattern and never ends, and therefore is irrational. Learning target number 2 says that you can explain why multiplying a rational number except 0 and an irrational number, and you're going to produce an irrational number every time. Notice that they said except 0. As we saw in that last practice problem, 0 is kind of our special case rational number that can go against this. But if you take any other rational number, it can be written as a fraction. But that irrational number you're trying to multiply it by cannot. So we're going to have to revert them to decimal form. And when you multiply by this number that never repeats itself in a pattern and never ends, then the product it's going to create is also never going to end and is never going to repeat in a pattern. Therefore, you're going to create that irrational product. And learning target number 3 says that you can explain why sums or products of two rational numbers are going to be rational. Think about it this way. If I am adding two rational numbers, then I am adding two things that can be written as fractions. And when we add fractions, we simply make sure that the denominators on the bottom are the same. We add the numerators on the top together, and we leave that over the denominator that is the same. Therefore, what we just created is now being written as a fraction, so therefore it's a rational sum. And kind of the same thing happens when we talk about products of rational numbers. We've got these two rational numbers that are written as fractions, and when we multiply across the top with the numerators, then we multiply across the bottom with the denominators, and what we create is a fraction, and therefore we create a rational product. So hopefully this has all made sense to you. Hopefully you found it helpful. If you did, in the bottom left of the screen, you should see another video that YouTube believes you will enjoy. In the bottom right of the screen, you should see the subscription button for the channel. Please subscribe to the channel if you find this material helpful. And as always, please give this video a thumbs up. And I look forward to seeing you in the next lesson.